Siwinski from Arteris, speaking on optimizing data transport architecture in RISC-V SoCs for AI, ML applications.
アルテリス・ミハル・スウィンスキー様より AI、ML アプリケーション向け RISC-V SoC のデータ転送アーキテクチャの最適化です。よろしくお願いいたします。
Great. Thank you all for being here. And, as some of the initial speakers said, RISC-V has come a long way, right? So by background, I was still am, I guess, an electrical engineering and computer science major from Berkeley. So the early days of RISC before RISC-V, more like RISC-II, that was still early. It was exciting. So were the early days of AI. In the 90s, right? But at the end of the day, it was very apparent back then, 30 years ago, that neither RISC-V, before that RISC-II, nor AI at that point in time were really ready for broad-scale deployment in real systems, right? So it's great to see how far we've come, particularly in the last decade, and how much all of this technology is getting adapted. So in this section with Arteris, I'll talk a little bit more about the underlying hardware infrastructure to actually make these systems possible and what we're doing around it. I'm going to start with a little bit of introduction of Arteris. I'm not sure if everybody is familiar. So very briefly, at a high level, Arteris provides the underlying connectivity, on chip and on die. So basically, we're the fabric that makes sure that all of this amazing IP, all these great processors and everything else that has to come in, actually gets stitched in such a way that you can get the right power, performance, and the end products to work. Another way to look at it is if you were to look at any kind of a die, or any kind of a chip, and you were to look at, well, what is actually what's what? So the gray areas is basically your standard IP blocks, right? And everything that's colored is basically what Arteris is. So it's that entire highway of information, of data that actually makes a chip or chiplet real. And another way to think about it, on average, about 10 to 13% of silicon is the actual interconnect or network on chip technology. Conversely, also the other part of it is the hardware-software interface, right? So register management, which is actually how you actually get the software to talk with the hardware, right? And that can be anywhere from 3 to 20%, depending on the vertical, right? So there's a fair amount of silicon that we're connecting on any kind of a given moment. So it's absolutely essential that we are optimizing our environment for the RISC-V ecosystem. So because we take this position of working kind of as the underlying connectivity, we work with everybody. RISC-V, yes, ARM as well. Everybody's a friend. We like everybody. And what that basically means is that it provides for interoperability and pragmatic changes in infrastructure, which I think is actually essential to a RISC-V adoption. And I'll talk about that a little bit more. Technology-wise, so we have seen our technology being utilized pretty broadly across just about every vertical. The observation has been that while this technology, this network on chip concept, it all started in mobile devices, 15, 20 years ago, but really the complexity has risen in everything. So nowadays, even things you would not think about needing this advanced connectivity, like IoT devices or microcontrollers, they actually do. So the complexity has risen to the point where this technology is actually utilized across the board. Now, the interesting thing about it is not necessarily that. The interesting thing is, if I look at across those verticals, across those markets, and I actually profile what is the actual percentage of the projects that are actually at this point in time AI in nature, right? be it for AI in general, machine learning, deep learning, pick your flavor of AI technology, right, and application. When we profile our traction last year, right, the observation was that almost half of the projects that were done globally had some flavor of AI technology in them, right? So AI has obviously become very prominent. And while you read the news, it's all about the software, and software is absolutely critical. The hardware also plays a key role. So looking at it a little bit closer. So of course, if you kind of take a perspective of normal progression over time, of course, all of you guys are familiar with these statistics, right? Where with the advancement of various architectures, we've basically seen that the peak compute has gone exponentially almost. We'll come back to the exponential later. DRAM bandwidth has increased, interconnect has increased, everything is increasing. And then, of course, you listen to David Patterson, go Bears, or Hennessy, Stanford. They'll say that obviously, while this is great, we're actually in a different inflection point. And indeed, that is the case. And so besides just feeling it and seeing in the projects, there is actually some data that supports this. So looking at AI compute, right? The interesting thing is we actually look at the compute performance in systems that has been really getting unleashed in the last several years. It is at a very different rate of progress than the technology it used to be in the past, right? So the typical Moore's law, right? Double the compute, right? We're now moving into a cycle where for the last several years, every 3 to 4 months, basically that net compute has been obsoleted. So the very fast pace of development is absolutely here. And conversely, that also means that the underlying complexity to build those systems, less so on the software side, but very much so on the hardware side, becomes a challenge to all of this. And as was mentioned earlier today, we have instances where the underlying algorithms that you do on the software side, there's many choices, right? While neural networks are, of course, great, and that's what, CNN is what you see in GPUs, right? Sometimes you can get great results with a basic, k-means or, just even trees will give you better results for some applications, right? So it's not about one size fits all. It is about a continuity of algorithms which actually will have increasingly divergent architectures, right? So the challenge is going to be, of course, well, how do you do something that will work for the AI technology of today and tomorrow and balance that versus really trying to optimize for a specific application? I think the result of that is going to be, which is what we're seeing, an explosion of both generic and specialized hardware for AI, where RISC is playing an absolutely, RISC-V particularly, is playing a very critical role. So looking at it more closely in terms of, some of the, basic things we're seeing with, RISC-V SoCs, more so than, let's say, in the different architectures, is that there's a couple of challenges. One challenge, of course, is making sure that there's the right level of support and compliance across a variety of standards, right? So unlike other architectures, here really the notions of choice and being able to deal with anything from various flavors of chai to the various flavor of ACE and being able to stitch those systems, no matter what the interface is actually one of the key paramount requirements. While, of course, sometimes it is easier to start from scratch, in reality, most projects don't really do that. There's a lot of reuse and there's a lot of evolutionary development. So making sure that you have an infrastructure that allows you to choose and plug and play the right thing to get the right performance, to get the right performance per cost, as we will discuss earlier, right, is absolutely paramount. Next bigger thing is, of course, dealing with the implications of the memory wall, right? So short answer is just bandwidth and wires that are involved, right? So that is going up. We was mentioned before here, of course, certification, compliance, validation, like ensuring ASIL B and ASIL D for mission critical applications. But then also taking all of those and making sure that you can actually still realize it in silicon, right? So being able to take all of these great ideas of algorithms, topologies, requirements, and actually give it to the backend team and making sure that in 5 nanometers or 3 nanometers, they can actually make silicon out of it, which is no longer trivial, right? This has gotten really, really complicated. So what is being done about it? So before we go there, I would just quickly, just from a technology side, because I'll be referring to this, right? With Arteris, it's really coherent network on chips. That's basically what you do to connect primarily to your CPU cluster, right? The non-coherent, which is you basically do for everything else. And typically that's, for example, how you'll be mostly connecting your NPU or just your AI accelerators with RISC-V, right? We're seeing a lot of that. Last level cache, very good for performance optimization, particularly for designs using high speed, high bandwidth memories. And of course, the register management, right? To making sure that that entire connectivity between the hardware and software layers, its documentation, its execution, all of that is flawless, because that's like the silliest way to have a respin, but it does happen. So one thing, okay, so with that in mind, so one thing we're seeing is that there is a lot of systems that are very heterogeneous, basically mixing and matching different kind of IPs. So of course there's many projects that are just RISC-V or just ARM. But in reality, we're also seeing pragmatically that many people are building combination projects and sometimes systematically replacing one type of IP or one subsystem with another subsystem that optimize performance better, right? So this is an example. This is in silicon, right? But this was an example from a couple of years ago. But this is an example where there's only multiple CNN implementations using RISC-V. There is different DPU from Cadence. There is various flavor of ARMs, right? All of it with very high requirements on AI on the automotive, on the ADAS side, as well as safety requirements, because this was an automotive chip. So kind of the combination of all the problems all at once is basically very common, right? Probably more common than people realize. So making sure that, of course, as you're building the systems, adhering to standards, to protocols, validation of it, and optimization of it is absolutely essential to really pragmatically get a lot of RISC-Vs into the market, because again, not everything is going to be just a dedicated die or chip. One flavor of that, if you just think about it for protocols, that basically pragmatically means that you want to have support for ARM ACE, right? ACE5, and most of the RISC-V vendors, including in this room, right? Also support, of course, Chi-B. That seems to be the more pragmatic of the current coherency standards for interfaces. But there are some advantages also in Chi-E, and of course, this will continue to evolve. So the notion becomes, okay, how do you make sure you have the right mix of all of them so that you can build interoperable systems and potentially upgrade from one core to another when the right new technology comes online? Okay, next dimension. So with generative AI and just any kind of natural language processing computing, right? So large language models, right? LLMs. What has happened is, of course, that over the last 2 years, as ChatGPT and we went to a 3.5, and that was happening with 4.0 and beyond. Basically, the number of parameters has exploded, right? We're now in trillion parameter configurations. The implication of that on the training set is basically that the actual bandwidth and specifically the width of the data buses to actually compute that has exploded, right? So how do you build systems that are actually dealing with, buses that are potentially, 1,000 bits wise, 2,000, 4,000, with the right interleaving to make sure you get the right performance. So this is a challenge that has come into existence really in the last 18 months on silicon. and it's accelerating. So this is something that we have to continue to pay attention to and work closely with all of the hardware and software suppliers to ensure it gets supported. Next part of that, if you think about it, the actually transport architecture, right? There is many advantages to various architectures and topologies for how the data will actually be floating to enable compute. Different things you typically do in a CPU cluster, different things you would do in NPU, TPU, and you other XPUs, right? So there is no one size that's one way that's correct. There's advantages in what do you want to be doing for various applications. And sometimes, and what we're seeing, for example, for AI applications, mesh tends to be pragmatic, but so is torus, so is trees, so are other mixtures of topologies. So making sure the right architecture is in place is absolutely essential to actually getting the right performance out of those amazing CPU cores that we were discussing here to have the right net impact. A couple of other small things that we've been doing also to support RISC-V AI designs. So one of them is, for example, as you deal with high memory bandwidth architectures, right? Two parts, right? So being able to interleave the channels, that's absolutely important, and being able with multi-lane reorder buffers, right? So you're now getting into architectural things, and I don't want to talk about necessarily this level of specifics, but understanding them actually has a huge importance on the net performance of the system, right? Without these things, you actually don't necessarily get that whole performance that one wishes to have. Another example that is just thinking about how you actually do communication of, multicasting, right? So being able to take information that you want to communicate and actually blast it to a variety of different locations, which actually is very efficient for net bandwidth and performance of the system, right? This is, for example, one application we're seeing in deep neural networks, where people want to be very quickly adjusting the weights and image maps, right? So again, there's more of those things, but those are some examples. Next part is also looking at things such as, for example, AI tiling, right? So being able to actually build these very compute AI subsystems with many tiles that are actually optimized for the right performance. So this is really for all kind of workloads, from vision from visions on edge AI all the way down to high performance servers. And it really breaks into two parts. So one of them is, of course, you want to take this approach of tiles on your CPU subsystem, right? So here's, for example, what we're working with a couple of the various RISC-V CPU providers in this room to actually have these systems. But basically being able to take a variety of CPU clusters and connect to up to a 512 CPU system on the CPU side, right? And the same thing applies on the NPU side, right? Where you actually try to build very large accelerators, and you need to take the notions of tiles and mesh together to, for example, compute up to, have up to 1,000 tiles, and potentially can go larger, but at that point you really want to go into multi-die. And kind of also to finalize all of this, of course, core technology is great, but then there's a question of how you also then converge that on the back end, right? So being able to do the right automation with physical awareness, so you can actually close those systems, right? Designs used to be kind of not too bad until 10 nanometers. Below 10, at 7 and below, wires are everything, right? At 5 nanometers or 3 nanometers, area doesn't matter. It's all about the wires, right? The wires dictate the performance. So how do you close the system? And as was mentioned before, which I'm not going to spend time on this, but of course, as you then apply this to things such as autonomous devices, right? L2 and higher, right? Of course, safety and compliance become absolutely paramount, right? So ensuring that you actually do have coherent systems that are safety certified, not only for ASIL-B, but all the way up to ASIL-D. Again, core requirements to make sure that you develop these systems in a meaningful fashion. So in summary, of course, we want to make sure that, we have to continue and we work with the entire RISC-V ecosystem. If there's anybody who's missing, we apologize. We can add more pictures on the slide. We work with everybody. making sure, of course, that all of those collaboration support are actually silicon proven, right? So take it to silicon, make sure this actually works before it scales. And prior to that, also making sure that the right level of interoperability, board designs, testing comes into place. And when we do that, we can see examples such as, we open with Tenstorrent, so just add a Tenstorrent here, right? Where actually they can take all of these pieces and build these amazing high-performance computing chiplets with this kind of technology. And at the end of the day, right, AI, ML is here. RISC-V is playing an increasingly important role. We're seeing that a lot. Making sure that the right requirements for bandwidth, interoperability are taking place is essential. And at the end of the day, these systems will be very, very heterogeneous in nature. And that's what we're seeing. And we need to all make sure as the RISC-V ecosystem to make sure that this right level of plug and play design is part of the, how we approach it. Because without that, we're not really going to get the scale that we all want to see for RISC-V. Thank you.
Thank you, Mr. Siwinski. Do you have any questions?
質問のある方は挙手をお願いいたします。
No questions? Then I have a question. So, things like the bus connection versus like NoC, right? And these are like two different methods of like that achieving the similar sort of things. What is your view of like that things like advantages and disadvantages?
Sure.
Two technologies.
Yeah, so fundamentally the traditional approach to dealing with this is a simple bus, simple crossbar, right? That's the basic way, the way people have been solving this problem. And if you think about, let's do an example that is not computer related, right? Think of phone lines, right? Think of before Cisco and after Cisco, right? So before you got into kind of networking technology that actually effectively figures out how the packets of information are there and moving, right? It was kind of different. Nowadays, all of us have voice over IP on our phones, and everything is routing properly, and we sometimes don't even know whether we are using Wi-Fi or a phone carrier for how our video or phone conversations are happening, versus before, right? You would know. Now you don't. So it's the same concept. I think the underlying traditional bus connectivity, the crossbar, it was very efficient back when you dealt with 10 pieces of IP. You were maybe at 0.5 micron technologies, right? And you really didn't have to worry about a lot of problems. You have to worry about deep submicron with all of this compute that has now been exploding. On the same time, you get into any kind of the compute complexity we deal with now when you have thousands of pieces of IP on any chiplet, right, or chip. And you have to worry about what at 3 nanometers, how you actually design that to actually make sure that's something that doesn't just melt during or blow up in the tester. That basically means you really got to be efficient about how you packetize and transform the data and transition data during the chip. Otherwise, it's just not going to functionally connect. Okay, thank you.
Hello, my name is Mandalay from Renaissance Electronics. So thanks so much for your presentation. I wanted to jump into slide 14. You had two versions of the same slide, one with the flex knock and one without. Could you talk to like the trade-off between one or the other?
Yes, so actually in both of these, flex knock is the one on the bottom, Encore is the one on the top. And at the end of the day, it really comes back to, see if I can remember the right slide, probably not. It really comes back to this dimension of it. Just go back to, sorry, here we go.
Right, yeah.
This dimension where at the end of the day, when you're dealing with coherency, right? Coherency basically requires a very different way of making sure that information is, how it's basically being connected and how it's being synchronized, right? So cache coherency requires a different set of protocol per se versus the non-coherent system. And because of that, you can make different optimizations as far as caching, as far as the actual optimization of the protocols. So at one point in time, we were looking at, can we build the one-size NAC that does everything, coherence and non-coherence? Is actually extremely inefficient for both. So at the end of the day, we're optimizing for coherence and non-coherence. And the simple way to think about it, if you're connected to a CPU where being able to deal with coherency, which basically means you're synchronizing the data, right? If that's something that's important in your system, that's great. Of course, there's overheads. There's overheads to your software. There's a price to pay for coherency and advantages. So not all systems are coherent, right? Conversely, non-coherency is more traditional, it's great. And for example, in AI application APUs, many of the actual algorithms don't require coherency because you actually transformers overriding the memory locally, right? So they're both good. There just depends on what you're trying to build. And a system that will have coherency, of course, has non-coherent systems in any instance. So it's a question whether you have both or one parts, depending on the architecture and application.
Okay, thank you.
Thank you, Mr. Siwinski. Next, we have Mr. Satoshi Tanabe from Synopsys presenting introducing RISC-V processor IP optimized implementations of the RISC-V ISA.